Okay, doors are closed, so I guess that means this is a good time to get going. I'd like to thank you all for being here. My name is Jason Hathcock, and I am a research scientist working at the Math Citadel with my co-founder, Dr. Rachel Traylor, here in the front. So, what I'd like to talk to you about today are storage failures, specifically that they're not independent, as you might have gathered from the title of this presentation. I'm also going to tell you what we can do about it to fix it and why it needs to be fixed. So here's a bit of an overview. I reiterate, storage failures are not independent, and there's emphasis on not, and what we can do about it. And I'll go into a bit of the theory we've developed in order to fix this kind of problem. And then, in the spirit of my co-founder's presentation earlier, I don't know how many of you were there to see it, why it's important to you. Why do you care? So, by getting started, I put this big sort of declarative, storage failures are not independent, and there's emphasis everywhere, bold letters, all caps words, and things like this. And you might be asking yourself, like, well, okay, who said they were, or like, what's the big deal? The thing is, a lot of the modeling around storage failures and the predictability of storage failures in all these models are assuming that they are. So here's a figure, a simple Poisson process. The current methods of analyzing storage failures of all kinds makes an assumption. The typical model says that the probability of capital T2 occurring at little t2, given that capital T1 occurs at little t1, where little t is standing for time here. These failure times, the probability that T2 is equal to little t2, given that T1 is equal to little t1, it's like T1 didn't matter, right? They're totally independent. It's the same as if we just said probability that T2 is equal to little t2. Had no bearing on each other, just like coin flips. This is just not the case. Now, I may have practitioners in the audience here, people that work in storage and know a thing or two about failures on the practical side. You may be telling yourself, well, I could have told you that. I know that you can't just say failures have nothing to do with each other as they occur in time, right? We have an idea of things called like cascade failures. And while I may not work in the storage industry itself, I can tell you that people are doing research in it as many as 11 years ago have showed that like latent sector errors are not independent. So your intuition is right, and the data agrees with you. Same thing can be said for disk failures overall. And the discrepancy between the model that is assuming that they are independent and what the data is telling you can be rather vast. It's underestimating. So what is it that we can do about this? Like I said, typically we use a Poisson process to count random events. This isn't just storage, this is done all over the place. This is in industries across the spectrum. And why Poisson process? Well, that's what it's for. That's what the model is designed to do. It counts random events. And there's a well-established history of using Poisson processes to count random events. The math exists, the math is easy to carry out, and it makes sense for the situation. But a Poisson process comes with a lot of assumptions. It comes with hypotheses. In order to assume that this is what you're modeling with, it has to meet the hypotheses of what a Poisson process is. And one of those, very important, is that called independent increments. Also said, these are assumed to be independent events, and according to the research, we know this to be false in the case of storage failures. So the usual approach does us no good here.
What do you mean by independent increment? I mean, I see independent event.
Mm-hmm. Well,
if you're counting events.
Mm-hmm. The way a Poisson process actually works is it's actually tracking the times. So it's a long time. So the increment between failures is another variable. The times between the failures is also what's being counted by the Poisson process. So those increments in time are what are being discussed. So is the Poisson model bad for this situation? Bad is not the right word. It's not bad. That's what it's designed to do. It's designed to count things. Why wouldn't we use a counting process to count failures and model them? It's just not general enough. It doesn't account for the fact of dependence of events, and it can't. It's assumed that they don't. So, in mathematics, we say that events A and B are independent to mean the probability of B is the same as the probability of B given A. It's the same equation we had a moment ago with the T2 and T1. And we say they're dependent if they're not independent. That's it. So if you're a person working and they need to put something to use and somebody tells you things are independent, you've got something. You have an equation you can work with. You can actually put it to work for you. We only say they're dependent if they're not independent. And that doesn't give you anything to work with. So if you come and tell me, well, I know these two events are dependent, I can say, oh, okay, well, I know an equation that will be of no use to you. And that's not really useful, is it? So this is a definition by negation. There are no concrete equations that go with it. It can't be put into practice, except we have a way to quantify dependence now. We can fix the fact that this definition here is not useful. And this brings me to our dependency theory. So this is something we've worked with for quite some time now, and we're putting it together still. It's an evolving theory. It's kind of a big deal to put together an entirely new theory in mathematics. It's a large undertaking. So I'm going to go through the thread of this dependency and how we work it into a mathematical construct that has before been presumed to show off independence. And I'm going to do it in a way that's a little simpler than taking the Poisson process we talked about before, trying to work through it that way. So let's talk about coin flips. This is something that, everybody can think of pretty, it's a nice visual, right? Suppose that we're going to call the probability of the heads on a coin flip P, and the probability of tails is what's left. 1 minus P is just Q. Normally, when you talk about a coin flip, these are both, if equal 50% shares, right? Half and half. They should be the same, unless we're talking about some kind of unfair coin. We introduce dependency by taking a number delta, a fraction between 0 and 1 inclusive. Could be 0 or 1 as well. And we define a few new values. So P plus, the plus superscript, is going to be P plus delta Q. So in the instance of plus as a superscript, we're always going to add delta times the other guy. So Q plus is Q plus delta P. And P plus is P plus delta Q. P minus is P minus delta P. So in the instance of a minus superscript, we take away delta times the same guy. So it's a little just to keep it straight, P minus now is P minus delta P. Q minus is Q minus delta Q. So we don't switch the letters on that one. And what's the point of all this? Like, well, okay, we're defining new values. What's the point? Well, normally, if you were to go through a series of coin flips, every time it would be, well, I got a 50% chance of heads. I got a 50% chance of tails. And every one of them is naturally independent of the other one. It doesn't matter, right? I'm going to show you what it's like whenever you introduce the fact that they could depend on one another. Strange as that idea may seem. So this is the probability mass tree for a series of coin flips that we've discussed. Normally it would play out like this when we talk about what we're going to call first kind dependence. So if you can imagine no dependence at all, P and Q would always be reiterated on every branching here. So the probability of each one would just be P and Q, P and Q, P and Q, P and Q. It doesn't matter, right? Like each one is independent of the previous one. What we're presenting in this case is first kind dependence. And when I say first kind dependence, it's because it's dependent on the first guy. So imagine that all of the coin flips that you do successively rely on the first outcome you got. So what's going to happen in this instance is you'll see if your first result on a coin flip was heads, you're going to weight towards getting heads ever after. The probability is increased towards getting heads ever after on each successive trial. And the reason for it is that first coin flip. And similarly for weighting away from the other guy.
When you put that notation,
Yes.
on the line joining the two probabilities, how did you come out to be either P minus or Q plus? How did you come out with that?
This represents all possibilities of the next trial. You're asking why are they in this order presented?
No, I'm saying that, okay, so take for example, you have a head, and then you get another head, and you put a P minus in between, right? On the third branch from the left.
Okay.
Fourth branch, I'm sorry.
From the left.
From the left, the fourth branch.
Okay, right here.
Yeah, come down 3 branches, 1, 2, horizontally.
Okay.
Okay. Okay. So you have a head there,
Mm-hmm.
and then you get a head back. How do you determine it's a P minus?
That's what
Bec-
independence means.
Right, because the first one following this path was that we assumed Q, meaning we had tails. So if the first one we got was tails, we are waiting away from any chances of getting heads now. So this is why you're seeing the minus on all the chances to get heads the ever after. We're waiting towards, with plus, the tails because that first guy was a tails. Does that make sense?
Yeah. Thank you.
It's a good question. Okay, so this is what we call first kind dependence, and this is the abstract version of it, where I've put my P plus and Q minus all across. Now let's consider some examples here, because right now P plus, Q minus, Q plus, these are all representatives of P's and Q's with deltas mixed in, like we said before. So let's bring it to some examples. Let's talk about first kind dependence in the instance that there is complete independence. Because if we have a model for dependence, it should be able to show us what happens when we don't have dependence. That's what our extremes are for. We'll also get to complete dependence as well. Example 1, complete independence, meaning that delta is equal to 0 and it's a half for P and Q. So just like a coin flip naturally. So if you put in your delta and P's and Q's, you see that it's a half every time. So now it's equal, just like you would have with regular coin flips. Complete independence. Now, of course, total dependence would be that it counts entirely on this first guy. Even if the coin is set up that it's 1/2 for P, 1/2 for Q, delta is equal to 1. So look at this. If you follow the tree from the first trial, if I flip and I got a heads, ever after, the probability that I get heads is 1 and 0 for tails, meaning that actually this branch, this pathway, after you've gotten that first head, is closed off. And here's something in the middle. Let's let P and Q both be 1/2 as usual and put delta at somewhere in the middle of the road, 1/2, between 0 and 1, as we presumed before. And you can see, just like before, if I get a tails on the first flip, then I'm weighting towards tails thereafter. So it's 3/4 instead of a half for the next tails, and so on. Of course, this one doesn't close off possibilities to us like this one does. Okay, so it's important to note that I have kept this to the instance of P and Q both being 1/2 because that makes sense for coin flips. There are such things as unfair coins, just because this is just an example of what is called a Bernoulli trial, where you have an on-off option, kept simple for the purposes of illustration. But this extends to more complicated examples. And of course, delta is allowed to be between 0 and 1, all inclusive. So this could get rather worse than 1/4 and 3/4 on the tree. It's worth pointing out that I just mentioned something called first kind dependence. Yes?
What you're describing sounds very much like Markov process. Like you go from one state to another, and it is defined by a transition matrix, right?
That's
No.
that's not correct.
No, no, that's not right. Well, what is happening here is this was Bernoulli trials, these are moving from one to another. These are just coin flips. So it's not exactly a Markov process where we're changing states.
But when you start with a tail, you
No, that's not quite right. What if you can clarify that question, we've reserved some time later to answer something like that, so if you've got more on that. But a point that you might make about that is, okay, you just said, what if it all depends on the first coin flip? Not only is that unrealistic, but I can't really think how that would fit my current situation. I don't understand why that dependence would make sense for my situation, and it may not. Now, you may see in your work that dependency follows kind of like dominoes. Like, it actually does matter very much what happens first, and that is very decisive in what happens next. But first-kind dependence is not all that we've developed, and it may not fit your case anyway. Dependence may follow a completely different scheme in your operations. And we have actually put together a rich class of dependence schemes by way of functions. So these are functions on the natural numbers. Basically, it tells you where to point backwards from your present trial to find the sort of reason for your dependence. Where does it originate? This is a diagram for first-kind dependence. Every trial, so you can see up to n, points back to the first guy. That's where all the dependence originated, right? But that may not be your case. Here's an example of what we call sequential dependency. So if you can imagine, in this instance, all trials point back to the immediate predecessor. So n points back to n minus 1, points back to n minus 2, and we get eventually to 3, to 2, to 1. So the dependency is actually threaded through much more complicated than it was with first kind, where you could just depend on the first result and follow that through the tree. And this one, you would do the same thing, but it's actually dependent on the immediate predecessor. And here's something just a little more complicated, and I like to make ones like this because I happen to do math. We're representing the function that assigns the dependence and tells you where it comes from by the floor of the square root function. So in this you can see that 3 and 2 both point to 1, but you follow the squares all the way up. So 4 through 8 will point to 2, 9 through 15 to 3, and starting with 16 will point to 4. Now, of course, we had to define a sort of set of hypotheses just for this to make these functions tractable and workable for assigning a scheme of dependence. And all of this can actually be found in our research papers on the site, mathcitadel.com. I won't go into too much detail on the construction of those, even though it was a lot of fun for me. But I'll move on. This brings me to why do you care? So I realize what I've presented so far is kind of a lot of mathematical abstraction, right? Like, okay, you've got a way to discuss how things are dependent. I see a lot of functions. I see a lot of trees, P's and Q's and deltas is very abstract. What is this? What is the reason for this? How does this affect me?
I just have one question.
Yes?
You have epsilon 1, 2, 3 on your graph.
Yes.
And what does that correspond to?
That's a fair question. Each one of those epsilons points is just the name for a trial, one of the flips. So we're just calling that epsilon. Working in mathematics, how many Greek letters did we wind up using? I think we had to use several other alphabets. I think we got into Hebrew and such. Okay. We're using dependency theory to generalize the Poisson process in the same fashion. What you just saw, what I showed you, was a series of Bernoulli trials. And that's not this, it's not the same thing as a Poisson process, I realize that. But we are using dependency theory to generalize the Poisson process the same way. As a matter of fact, at this very time, we've already generalized several probability distributions to account and work in dependence and still get a lot of desirable properties. So let's see, I can think of at least 4 right now. We've got binomial, negative binomial, multinomial, and we've extended this result to cover any discretely valued probability distribution the same way, which will include, in future papers, the Poisson process. And why do we want to do that? Well, it amounts to the features of the Poisson process are desirable. Like we talked about earlier, It's what we want. We want to count things. We want to count these random events. It makes perfect sense. There's a whole bunch of theory developed on the fact that we have a Poisson process to use. It's just we didn't have dependency worked in, and for these models to assume that you're pulling all of these failures from the same distribution and its independent increments, and they are independent and identically distributed, it's just not the case. But what if we can make a distribution where we can say, well, they are dependent but identically distributed. They're dependent, and the dependency is threaded throughout the entire thing. You can still use it. You can account for that dependence, and you can make a model based on that. What do you get? You get a better model, one that's more understandable. This isn't like a black box algorithm. This isn't something that you can't understand what's actually going on the inside. You actually know exactly how it's working. It's just like the model you're using before, except it accounts for something that you weren't accounting for. You get improved reliability predictions, naturally, more to mirror the results that the data is telling you. And it explains how the failures are dependent, not just if they are. So there are measures for determining whether the data you're bringing in probably are dependent, but it doesn't tell you how. And we've actually got an entire class of functions that can represent exactly how your data are dependent. It's a wealth of them. So it answers the question how, not just if. And with that, I would like to mention that the applications of this fundable research are unclaimed. That's kind of how we work. We have a way to make these models better. We have a way to make them more accurate and more reliable. And what we are offering are the applications of such models. Now, I'd like to bring up my co-founder so that we can answer any of your questions on this.
Yes, that's probably it.
Yeah, that's what we've got.
So, thanks for that. That was probably, like I said, pretty abstract talk, but thanks for coming.